All right, so this unit is chemical reactions and types of reactions and equations. So today we're just going to refresh our memories on how to balance equations and talk about equations. Next week we're going to do types of reactions. So I'm going to tell you there's 5 basic types that we're going to be responsible for, and you will be predicting what they make. Okay? So today you're going to have reactants and products, but next week you're going to be predicting the products. Okay? So if you are still struggling with writing your formulas, remember I've been telling you, you've got to learn this or it's going to bite you in the hiney. It's going to bite you in the hiney. Okay, so you've got to have those down, okay, because we're going to be using those for the rest of the year. So let's get started. So first of all, very basics. When we're looking at a reaction, I want to make sure that you know where the reactants are located and where the products are located. Because there have been times when I'm talking about a product and there are students talking about the reactant. So when I'm looking at an equation, in terms of where the arrow is, where are the reactants? Before or after the arrow? Before. Yeah, before the arrow. They are before the arrow. So that means the product, you can move up, the products are after the arrow. Okay? So when I am looking at a reaction, it's reactants, I'm going to abbreviate, goes to products. And I know that seems fairly basic, but there have been times when people get them confused. So I'm just going to clarify that right now. Okay? The reason that we balance equation, actually a lot of the reason for chemistry itself, is because of the law of conservation of mass and mass and energy, or matter. So basically, whatever I start with, I have to end with. If I start with 15 grams of my reactants, I have to end with 15 grams of reactants. If I start with 5 atoms of carbon in my reaction, I must end with 5 atoms of carbon. Otherwise, I'm defying the laws of nature. Okay? So what that means is that the same number of each atom must be on both sides of the equation. Okay? All right, so now that we got that part, let's go to C. The state of matter should be indicated for each product and reactant. I'll show you that in a minute. It's supposed to be, and most of the time we do it, and on your worksheets you'll sometimes see it, but when we're writing and balancing and predicting, I'm not going to ask you to write every little thing because it gets tedious, okay? But on some of the products, you will have to tell me whether it's a solid because it tells you if that reaction happened or not. So as we go along, I'll tell you, don't worry about it, or yes, worry about it, okay? But I need you to understand and recognize that. Remember when we're doing our reactions and we have one of the Brinkelhoffs, they're diatomic. And so if they're by themselves, you'll write them like Br2, H2, O2, etc. So make sure you write that. Not when it's in a compound. It can be anything it needs to be in a compound. But by themselves, if it's one of those diatomics, or what we lovingly call the Brinkelhoffs, you've got to write them as a subscript of 2. Okay? Also, all chemical reactions are accompanied by some sort of change in energy. It can either be producing energy or absorbing energy. Raise your hand if you remember which one is producing energy or releasing energy. Yes, Abigail. Exothermic, right. And so if it's an exothermic reaction that's releasing energy, it will appear as a product, which is going to be slightly more important when we get to thermochemistry next semester, but it doesn't hurt to see it now. So exothermic is producing or releasing, so that leaves endothermic as absorbing, and which we would treat as a reactant because I had to add it to the system. Okay? So, the things that you might see in a chemical equation. First of all, when we are separating 2 or more reactants or products, we do a plus sign. Make sense? That's a poor plus sign. Let's make that better. Okay? When we are saying what the products may, we use that arrow, but it does not mean equal. It means yields. So if I was going to tell you that sodium plus chlorine yields sodium chloride. Okay? In place of, for a reversible reaction, sorry, I was getting ahead of myself. A reversible reaction we're going to show with a double-headed arrow. And in fact, most reactions in the world are reversible. Okay? When we get to equilibrium, you'll exclusively see that double-headed arrow. And that means that the forward reaction is happening, but so is the reverse reaction. Okay?
What do you mean by forward and reverse reaction, though?
Read it forward, read it backwards.
Oh, so it's kind of like.
How about we wait till we actually get to reaction and I'll show you. Okay. That'll make more sense. Okay? If we're going to designate that something, as a reactant or a product, is in the solid state, we're going to do a little tiny little s in parentheses behind that reactant or product. Okay. An alternative to the S, but used only for a solid product, not with the reactants. And usually we use this when we had a precipitate produced. So we started out with two liquids, mixed them together, and I formed a solid. And what happens when I form a solid in some liquids? What will the solid eventually do? Fall to the bottom of the container, so we draw that as an arrow going down. If I produce a solid, solids are going to be generally heavier than the liquid, so it'll fall to the bottom of the container. Okay? For a liquid, we're going to do an L, but we're generally going to do that a little cursive L or italicized, because if I just do a regular run-of-the-mill lowercase l, it looks like a 1. So we usually do that as a little cursive L, so we can see liquid, not 1. You already recognize aqueous. How do I write aqueous? AQ. Y'all are smart cookies. What do I do for gas? And the alternative to a G would be an up arrow, yeah, because what happens when you produce a gas? It goes up out of solution. It bubbles out of the solution, so it goes up. Okay? If I am needing to show that I heated this reaction to happen, because some reactions won't happen unless I heat them, I draw my yield arrow, and then it's a triangle above, and that just indicates that we heated it. And then the last one is if a catalyst was used, and a catalyst is something that speeds up the reaction. It doesn't actually participate in the reaction, but it provides another pathway for it to happen faster. And so we draw that arrow, and platinum is a very common catalyst, so we would put the symbol above it. Or let's say I was breaking down water with electric current. I would draw like an arrow, and I would like put ELEC for electric or electricity, meaning I got that reaction to happen by providing a catalyst of the electricity.
So instead of PT, we would put like just their...
Whatever it is, you put whatever it is.
So like if it's, say like potassium, we would just put like a K or anything?
Yeah,
like that?
potassium would never be a catalyst. It's too reactive.
Okay.
I don't want you to think it can be. Potassium is a group 1 metal, most reactive. It would not be a catalyst. Okay, so before we start balancing, I got to make sure, again, the simple stuff, just to in case someone's confused. So first of all, we need to be able to take an atom count, and we need to know what the subscripts are and what the coefficients are. Okay, the subscripts, of course, are the small numbers in the formula. They only apply to the element that's right before it. Okay, so for this first one, I've got magnesium chloride. That 2 only goes for the chlorine. So that means I have 1 magnesium and 2 chlorines. In the next one, SN3 and 2, the 3 only counts for this tin, the 2 only counts for the nitrogen. Okay, so when I have a subscript, it only counts for what's right before it. If I have a polyatomic in parentheses with that number out there, I distribute that on the inside. Okay. The coefficients is what we're going to use to balance our equation. They're the big numbers in front. Okay, and so when I have a coefficient, it counts for everything that comes behind it. Okay, so not just the one that's near it. So this 3 doesn't just count for the sodium, it counts for the whole darn thing. Okay, so we're going to do some simple math here, and you're going to tell me how many sodium do I have in that right there. So if I'm looking at this, how many sodium do I have? 6. How many sulfur?
3.
And then how many oxygen?
12.
12. I multiply my coefficients and my subscripts. Okay, I multiply. And I know on your notes there's a typo. It doesn't say atoms of calcium. It says atoms of sodium, so change that to Ca. I thought I caught that. I caught it on this one, but not on your notes. Okay, so in this case, Isaac, how many atoms of calcium do I have in this?
3. Oh,
12. Okay. All right. Isabel, how many phosphorus do I have?
8.
8. And let's go with Sharia. How many atoms of oxygen do I have? 32. Okay. If there's anybody that doesn't know where I got those numbers, tell me now. Okay. Notice that I, first of all, had to multiply these two. That 2 outside goes for everything inside. So really, for that particular one, if I'm looking at PO4, the fact that I have 2 of them, I have 8 oxygen and 2 phosphate, and then I multiply that by the coefficient of 4. Just make sure y'all understand that. I know some of that seems pretty basics, but sometimes if I skip those little things, people are like, I don't know what she's talking about. So sometimes got to include the simple stuff. Okay, so when we're writing and balancing equations, okay, when we're balancing them, like I've given you an equation, you're just balancing it, that's different. But if you're having to write them, which you will be writing a lot of them, mostly you will be writing these, there's a couple of things we have to remember. One is once we write the equation using the correct formulas, that we're going to never change them again, okay? So once you write the correct formulas, you do not change them, because what happens is sometimes people say, oh, I need 2 chlorines, and so they'll go it's NaCl, and they go, but I need 2 chlorines, so they'll go NaCl2. You can't do that. First of all, it doesn't exist. We're not allowed to do that. So this is where I make you take an oath, because I'm serious about this. So everybody raise your right hand. Come on, participate. Raise your right hand and say, I do so solemnly swear
I do so solemnly swear
that I shall never,
that I shall never,
ever,
ever
change the subscripts.
change the subscripts.
Okay, the end. Okay.
So maybe.
Providing that you wrote the formulas correctly. Now, if you've written out this formula, you've written out all the formulas, and you're trying to balance the equation, and no matter what you do, you spend 10 minutes on trying to balance this equation, do go back and double check that you wrote your formulas correctly, okay? Because if you didn't write your formulas correctly, you'll never be able to balance it, okay? But if you know your formulas are correct, you do not change them, okay? And I can't tell you how many times kids try to do that. They'll think, oh, I need 2 chlorines. Let me throw 2 on the end. No, that doesn't exist, okay? All right, and we always only balance the equations using the coefficients. Okay, hints to balancing, okay? You can look up things and they'll tell you, some people say, oh, just balance the metals first. Just balance this first, balance that first. I say, balance what you notice first. Whatever your eye is drawn to, balance that first, okay? If you want to come up with a process that I always balance metals first, and then I do this, and then I do this, that is perfectly fine. But I find that kids have more success if they balance what they notice first, okay? So write that down if you want. I mean, it's not that big of a hint, but I'm just telling you, balance what you notice first. But this is a very big hint, and it'll make your life easier, and that is treat polyatomics as one unit. And what I mean by that is, let's say I have SO4 2 minus, and I've got that in there, or yeah, I've got calcium sulfate and it's in there. Balance the sulfate as one unit. Don't try to balance the sulfur and the oxygen separately. It makes it way more difficult. Because if I have sulfates on both sides and I just use my coefficient to balance them, they take care of themselves. Even if there's other oxygen or other sulfur in there, if I know my sulfates are balanced, then they take care of themselves. So do not try to break them up and balance them individually. Unless the sulfate itself broke down into something else, then that's a different story. But if I have the same polyatomic on both sides of the equation, treat it as like you would an element, like use a coefficient, okay? And then when we get to a combustion in a minute, I'm going to give you a hint that's just for combustion reactions. So we'll do that in a second, because if I try to tell you it now, it won't make any sense to you. All right, so let's practice. Now, in junior high, they may have made you write like an atom count, like list out hydrogen, oxygen, and do your atom count. You do not have to do that in here, okay? If you want to and it makes you feel better and it's like your little security blanket, go for it. I won't even make fun of you for it, okay? But it's usually faster to not do it that way, okay? But I've had students that really like to do it that way. One of my top AP students that I've ever had, when he was learning how to do it, he was very methodical and meticulous, and he liked doing it that way, and it worked for him. So if it works for you, go for it, okay? If not, don't do it. It makes them a lot faster and easier. Okay, so I'm going to look at this, and I'm going to say, first thing, I have a hydrogen, 2 hydrogen, reactant side, 2 hydrogen, product side. So my hydrogen is currently balanced. And then I check my oxygen. Oxygen is 1, oxygen is 2, not balanced. How can I fix that? Tell me. Shreya?
Put 1/2 on the coefficient.
No, we're not going to use fractions in here. Yeah. You can use fractions, And in AP we do use fractions.
We use decimals?
But never. We're not going to use fractions. We're going to use whole numbers because if we start using fractions, it confuses the masses. So we're going to stick with whole numbers. In AP, we have to use fractions for balancing. But that is good. That's like thinking outside the box. But it confuses too many people if I start using fractions. So we're going to keep it as whole numbers in here. If you have a chemistry teacher, or not teacher, but chemist or whatever at home, and they help you sometimes with your homework and they tell you fractions, just say, yes, my teacher said I know we can, but we're keeping them in whole numbers for here. Now, if you did it on a test and it was right, I'm not going to count it wrong. But it confuses the masses. So what do I want to put in front of water?
So do you want me to say the whole thing?
Sure.
So you put a 2 in front of water and then a 2 in front of the hydrogen and then just a 1.
Yeah, and if it's a 1, you don't have to list it. Just leave it blank. Yeah, because we're assuming it's 1 because we wrote it down. Yeah. So it'd be 2 in front of here because that took care of that oxygen over there. It's the only thing I could do. And so, of course, when I put the 2 here, it made it be 4. So I can make that be 4 by doing that. Okay? Any questions on that? Okay. Let's do the next one. What do you notice first?
The polyatomic.
Yeah, but what do you notice it's not balanced first? Sodium's right here. 1 sodium, 1 sodium. It's currently balanced.
Oh, the lead.
Lead, 1 lead, 1 lead, currently balanced. The nitrate, thank you. The nitrate's not balanced. I have 2 nitrates here and 1 nitrate there on the product side. So the only way that I can balance my nitrates is to do what? Put a 2 in front of the sodium nitrate, right? Yeah, you got it, you got it. So when I put a 2 in front of the sodium nitrate, what did that do to my sodium?
That makes it.
So now I can fix that by putting a 2 there. Now am I balanced? 1 lead, check. 2 nitrates, check. 2 sodium, check. I'm balanced. Okay? Any questions on that? Why and what we did?
That makes sense.
Okay. The next one is, this is letter C. This is a combustion. So this is where I'm going to give you a little tip. Okay. Combustion reactions are the easiest ones to predict, but they're a little bit trickier to balance. The way I know that it's a combustion is this right here is called a hydrocarbon. Why do you think it's called a hydrocarbon?
Because it's hydrogen and carbon.
Hydrocarbon. There we go. Okay. And in order to burn anything, what do I have to have? Oxygen. So combustion will always have a hydrocarbon plus oxygen. And they always make CO2 and water. So they're the easiest to predict because if it's a combustion, it makes CO2 and water. Okay? But there's a problem with this in that balancing it becomes, got to play a little trick. Okay? Because O2, no matter what I put in front of O2, it's always going to be it's always going to be diatomic. But no matter what I put in front of there, if I multiply it, it's always going to be an even number, right? I can never make that O2 be odd unless I'm using fractions, but we're not doing that in this level. Okay. Same thing with the CO2. No matter what I put in front of there, my oxygen is always going to be even. But water is odd. Okay. I can never make my evens be odd, so I'm going to have to make my odds be even. So the trick is, go look at what your hydrogen is and see what you would have to put in front of water. And so for this, to get it to balance, I would have to put a 5 in front of water. That's not going to work because it's odd. So what I'm going to do is I'm just going to bump that up and use 2 of them. Okay? So now let's balance it with 2. Sometimes you have to bump up and maybe go 3 or 4, but usually 2 is good. So if I have 2 of those, now, JT, what do I need to put in front of water?
20.
I need 20, but I already have 10. Right. No, I knew what you're going. So because I need 20, I got to put a 10 in front of water. All right. Kayla, how many carbon do I have now? 8. So I'm going to put an 8 right there. All right, Riley. How many total oxygen do I have on my product side now? 26. How did he get that? 8 times 2 is 16 plus the 10 over here for a total of 26 oxygen. So, who do I want to pick on now? Arthur. He just threw you under the bus. All right, Arthur, what do I need to put in front of oxygen to get 26? 13. Now let's double check everything. I have 4 times 2. I have 8 carbon. Check. I have 20 hydrogen. 10 times 2 on the product side. 20. Check. And then 26. And we already know we have 26. So check. We are balanced. Good luck on your thing. Okay. All right. Are we good so far? All right. If you're dazed and confused, you need to ask questions. I can't tell if y'all are just really paying good attention and you understand it, or you're like, I don't know what she's doing.
So you got 13 by dividing 26 by 2?
Well, yeah, because I have this 2 right here.
Okay.
Yeah. Yes.
Why did you multiply water by 10 instead of 5?
What?
Because at first you were like, you can multiply it by 5.
Oh, why did I not put the 5?
Yeah.
Because then this would be odd, and I would have an odd amount of oxygen, and I can never make this be odd on the reactant side. Because no matter what I put in front of O2, it's always going to be an even number. Does that make sense? Yeah. I mean, we're in AP, we're allowed to use fractions, but I just don't do fractions in here. It confuses people. So we just stick with whole numbers. Okay. All right, now let's write some. Iron plus sulfur is going to yield iron 2 sulfide. How do I write iron when it's all by itself?
Iron 1.
Just Fe. It's an element. It doesn't have a charge. When it's a free element, there are no charges. They only have charges when they're ions, and iron by itself is an element. Okay? How do I write sulfur by itself? Just an S. It's a yellow powder. And then I'll write what it tells me to write, which is iron 2 sulfide, which is FeS. Everything's a 1-to-1 ratio. Those are happy. When you see that, do a little happy dance. It makes life easier, especially when we get to stoichiometry. All right, zinc. How do I write zinc by itself? Zn. No, not 2 plus. Just zinc. By itself, zinc does not have a charge. This is an element. Okay? How do I write copper 2 sulfate? CuSO4. All right, and then that's going to yield zinc sulfate. How do I write that? Nope, not Zn2. Zinc's a plus 2 when it's in a compound, so it'd be ZnSO4 plus just a little old copper all by itself, no charge on it. Okay? This is a single replacement reaction that we'll learn about next week. Okay? All right, let's see what's on the next page. All right, I'm going to skip number 4 because it all ends up being 1-to-1, but I do want to do number 5. Ferric, that's the old naming system. Ic means the higher of the charge, so it's going to be a plus 3 for iron. So how do I write iron 3 chloride?
Fe3.
No. FeCl3, because chlorine is a -1. Okay, and then how do I write ammonium hydroxide? NH4OH. This is why y'all had the highest test average. Y'all know your formulas. Okay, how do I write iron 3 hydroxide? And then ammonium chloride?
NH4Cl.
Okay, now we write all our formulas and now we balance it. All right. JT, what's the first thing you notice that's not balanced? Hydroxide, good job. Okay, so hydroxide's got 3 over here, right?
Mm-hmm.
So I can only fix that by putting a 3 where? Right here, in front of the ammonium hydroxide. So now I have 3 ammonium and 3 hydroxide, but I only have 1 ammonium on the product side, so what do I need to do? 3. And then what did that just do for my chlorine without even trying? I balanced it, like magic. Right? So now, do your count when you think you're done. 1 iron, 1 iron. Check. 3 chlorine, 3 chlorine, check. 3 ammonium, check. 3 hydroxide, done. Okay? Any questions? All right. Then that concludes this portion of the lesson.
Yay.